Hello, this is Dr. Strickland. In this video, we will investigate the basics of acids, bases, and salts, and talk about determining the pH of an aqueous solution. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video, so that you're ready for the more difficult things we will do together in class. So some or all of this may be review for you, which is fine. I just want to make sure everybody has what they need. So we begin with the definitions of acids and bases that came from Arrhenius. And he said that an acid is a compound that will donate hydrogen cations when dissolved in water, and a base is a compound that will donate hydroxide ions when dissolved in water. And remember that a hydrogen cation, when it's dissolved in water, exists as a hydronium ion. So you'll see that also. Okay, so in terms of examples, I pulled hydrochloric acid. And hydrochloric acid is an example of a strong acid. Strong acids ionize or dissociate 100%, which is represented by a single arrow from left to right. And so the products are the hydronium ion and the counter ion from the acid. And this tells me that when we get to the end of this reaction, that essentially we've got all of these and none of those. Now, if you have a weak acid, something like acetic acid, H2C3O2, when it dissolves in water, it doesn't dissociate all the way. In fact, it's something less than 100%, very likely more like 10%. But what happens is it sets up an equilibrium with two products, and you do the products the same way as up here. The products are always the conjugate acid of the base on the reactant side and the conjugate base of the acid on the reactant side. So here we have hydronium ions, which is the conjugate acid of the base, and then the acetate ion, C2H3O2, which is the conjugate base of the acid. So this hydrogen here is put to the beginning of the formula to say that this is an acidic hydrogen. It's able to be removed by a base. And so that's a usual position if you have chemical formulas written like this, not so much if they're written like a structural formula. All right, over here on the base side, if you've got a strong base is the only one that don't show water as a reactant. In fact, it's just over the arrow to say, hey, this happens when you dissolve it in water. A strong base will dissociate or ionize completely into its component ions. And so you can write the hydroxide symbol like this. Sometimes it's written like this because the negative charge is actually on the oxygen. Either way, it's fine as long as you know the difference. All right, an example of a weak base would be an amine. And weak bases react with water to set up an equilibrium, very much like what we did over here with weak acids. It's just that the products are a little different, and you end up, instead of ending up with hydronium ions, you end up with a hydroxide ion, because when you've got a weak base, then the water is the acid. When you've got an acid, the water is a base. All right, so I did want to mention to you that carboxylic acids are very common weak acids, and amines like ammonia are very common weak bases. All right, so with salts, all salts are ionic compounds that involve a cation that is not the hydrogen cation and an anion that's not hydroxide. All salts are strong electrolytes, and they are formed by acid-base reactions. And remember that a strong electrolyte is something that dissociates 100%. So we're talking about strong acids, strong bases, and salts to whatever extent that they dissolve in water. Now, for the ones that are soluble, that means that they dissolve 100%. Okay, so things like potassium bromide or magnesium nitrate. And the solubility rules will be your best friend here to know which ones are soluble or not just by looking at the formulas. But again, just like with the strong bases, we're going to put water over the arrow. And then to the right of the arrow, the anions and the cations with whatever coefficient they should have that came from here. Here we've got one cation, one anion, so the coefficients are 1. Here we've got one magnesium and 2 nitrates. So 1 magnesium and 2 nitrates, and you do have to know their symbols and their charges. So this comes from its position on the periodic table. The polyatomic anions, you're just going to have to know. So if you haven't thought about those in a while, dig out your polyatomic anion list and refamiliarize yourself with those. Now the insoluble ones, I picked mercury 2 chloride, and I picked iron 3 hydroxide. And again, since it's a salt, I'm going to put the water over the arrows, but you can see it's the double arrow of an equilibrium and not the single arrow, because insoluble salts, they dissolve just a little bit. Now, whatever dissolves does dissociate. So I'm going to put the S subscript here for solid, and then, like, you can figure out some of these charges. Like if you know the chloride is -1 and there are 2 of them, then this has to be the mercury 2. And we'll have more to say about insoluble salts, but not right now. All right, then iron 3 hydroxide, the 3 is in the name, but you won't see that in the formula. But again, since hydroxide is a -1, you can figure out that this is the iron 3. Some of those transition metal cations have more than one charge possible, and you have to know which one you're dealing with. All right, so another concept that you're going to need that I suspect you've encountered before is conjugate acids and bases. And so I just want to remind you that a conjugate acid form of a compound always has one more H+, one more hydrogen cation than the conjugate base form of that compound. So we'll have one more hydrogen in the molecular formula, and this will change the charge by a +1. All right, so the acidic hydrogen, this one more H+, will usually be bound to an oxygen, nitrogen, or halogen atom in the conjugate acid. So if you've got a conjugate acid, it's phosphoric acid, we're going to take away an H+, right? Removal of a hydrogen takes this subscript from a 3 to a 2, and it goes from a neutral to a -1, or an uncharged to a -1. If you start with a conjugate base, now you got to know where the acidic hydrogen goes. And remember that with any base, we're talking about adding it to an atom that has a pair of non-bonding electrons to give. So that will usually be an oxygen or nitrogen or a halogen, chlorine, fluorine, bromine, iodine. So the conjugate acid of this ethylamine is the ethyl ammonium ion. And you can put the plus here, or you can put it over the nitrogen. Doesn't make any difference at all. All right, so here, if we have sulfate, that's the conjugate base. It's got to have one more H+, so we'll put a hydrogen into the formula, and then a +1 goes into the charge, so this is -1. So you see that conjugate acids can be uncharged, they can be positively charged, they can be negatively charged. I don't know of any conjugate bases that are positively charged right off the top of my head. They're usually either uncharged or negatively charged. All right, and finally with the hydronium ion, you take away an H+, goes from 3 hydrogens to 2, and the charge goes from +1 to 0. Okay, so just remember what you know about acidic hydrogens and basic sites in a molecule, and you'll be good. All right, so the pH system that we use to express the relative acidity or basicity of an aqueous solution comes from the self-ionization of water, which means that if you have water, and sometimes it's written with a coefficient of 2, I'm just gonna write it out like this so that you can see better what's happening. In the self-ionization of water, one molecule acts as the acid and donates a hydrogen cation. The other molecule acts as a base and accepts it. So if this one is the base and this one is the acid, then I can write my products like this: hydronium ion plus hydroxide ion. And when I write the equilibrium constant expression for this, the two solutions will go in, but pure liquids don't show. So this equilibrium constant has a special subscript. It's called Kw for water. And so it's the equilibrium concentration of the hydronium ions times that of the hydroxide ions. And they are a specific value at a particular temperature. So it's 1.00 times 10 to the minus 14 as long as you're at 25 degrees Celsius. So if the temperature changes, the value of this equilibrium constant will change. So because this relationship turns out not just to hold for this, but for any aqueous solution. If you know its hydronium ion concentration, you can calculate the hydroxide and vice versa. And you can also get to the pH. Now, pH stands for power of hydrogen, and there are other P values besides pH. pOH will come up a lot for us, but there are a bunch more for other kinds of cations and anions. Generally, the pH scale goes from 0 to 14, although I have seen solutions that had a negative pH, and I guess theoretically you could go a smidgen above 14, but in practice, mostly it's between 0 and 14. So, and pH is calculated as the negative base 10 log of the hydronium ion concentration. And so if you knew the pH and you wanted the hydronium ion concentration, you could rearrange this equation like this, 10 to the minus pH. And remember where you find the significant figures in a pH, because that's a logarithmic value. All right, so let's take a look at a sample here. What's the hydronium ion concentration in an aqueous solution with a pH of 5.65? And then is this solution acidic, neutral, or basic? All right, so a basic solution, just while we're here, is going to have a pH greater than 7.0. And a neutral solution will have a pH exactly equal to 7 point, however many zeros you want to have after that. And an acidic solution will have a pH that's less than that middle value. So you can already make a decision about classifying this solution. You can see that it fits here. It's an acidic solution. All right, so let's do the hydronium ion concentration. So we know that the pH is 5.65, and then you could get to the hydronium ion concentration by doing 10 to the minus pH, which in this case is 10 to the minus 5.65, which is 2.2 times 10 to the minus 6. And whenever you have these square brackets, that tells you that the units of concentration are molarity. And I kept two significant figures because all of the significant figures in a logarithmic value are over here in the mantissa to the right of decimal. All right, so that is the basic story on the beginnings, anyway, of acids and bases and salts and pH. If you have any questions, please send them to me.